This time, I'm going to show you how to formulate a linear programming model and solve it using graphical method. As an example, we're going to use a classic linear programming problem from the book Operations Research, an introduction from Hamdi Taha. It is known as the ready mix problem. So let's read the problem. Ready mix produces both exterior and interior paints from two raw materials, M1 and M2. The following table shows the basic data of the problem. So we have two resources, raw material 1 and raw material 2. For every ton of exterior paint, it requires 6 tons of raw material 1 and 1 ton of raw material 2. For the interior paint, it requires 4 tons of raw material 1 and 2 tons of raw material 2. The maximum available supply for raw material 1 is 24 tons and for raw material 2, 6 tons. The profit per unit of the exterior paint is $5,000 and for the interior paint is $6,000. A market survey restricts the maximum daily demand for the interior paint to 2 tons. The daily demand of the interior paint cannot exceed of the exterior paint by 1 ton. Ready Mix wants to determine the best product mix of the exterior paint and interior paint that will maximize the daily profit. The first thing we're going to do is to formulate an equivalent LP model of this problem. So the first step is to determine the objective of the problem. So the objective of this problem is to maximize the daily profit. The next step is to identify the decision variables that will directly affect the quantity we want to maximize, which is profit. Profit is directly related to the number of exterior paint and interior paint produced daily. So we let X be equal to tons of exterior paint. And we let Y be equal to tons of interior paint. From these two decision variables, we're going to formulate the LP model, which consists of the objective function and the constraints of the problem. So the objective function is, so we maximize, we let P be equal to the profit equal to, for every ton of exterior paint produced, the profit is 5,000. So that is 5,000 X. Plus, for every ton produced of the interior paint, the profit is equivalent to 6,000. So the profit contribution of every ton of the interior paint is 6,000. So all in all, that's 6,000 Y. At the same time, we're also going to formulate the constraints of the problem using these two decision variables. So we have 4 constraints for this problem, 2 coming from the raw materials based on the maximum daily available supply, and 2 coming from the daily demand of the interior and exterior paint. So for the constraints on the raw materials, for every ton of exterior paint, you need 6 tons of raw material 1, and for every ton of the interior paint, you need 4 tons of raw material 1. So, and daily, you have a maximum supply of 24 tons. So if you produce X tons of exterior paint and Y tons of interior paint with this requirement, the total daily usage of raw material 1 is 6X plus 4Y. Since the maximum available supply for raw material 1 is 24 tons, and we cannot exceed this quantity, the equivalent inequality for that is less than or equal. So our corresponding constraint for raw material 1 is 6X plus 4Y less than or equal to 24. In the same manner, for raw material 2, as a constraint, so maximum available is 6 tons, and exterior paint requires 1 ton of raw material 2, and the interior paint requires 2 tons of raw material 2. Its corresponding constraint is X plus 2Y less than or equal to 6. So our second constraint is X plus 2Y less than or equal to 6. And the third constraint will be coming from this statement. A market survey restricts the maximum daily demand of the interior paint to 2 tons. So interior paint, the number of tons of interior paint is Y, and it is restricted to a maximum value of 2. So that's less than or equal to 2 tons. So our third constraint is Y less than or equal to 2. And the last constraint is the daily demand of the interior paint cannot exceed of the exterior paint by 1 ton. So again, interior paint is Y, cannot exceed, so a maximum value that's equivalent to a less than or equal, and the exterior paint is X, cannot exceed the exterior paint X by 1 ton. So the constraint is equivalent to Y less than or equal to X plus 1. And converting this into a standard form, we transpose X to the left side. So that is equivalent to negative X plus Y less than or equal to 1. And to all linear programming problems, we require our decision variables to be greater than or equal to 0, which is the non-negativity constraint of every linear programming problem. And this is the equivalent LP model of this problem. So the equivalent LP model of the ready mix problem is this one. So the objective function is to maximize P, which is profit, equal to 5,000x, the profit contribution of the exterior paint, and 6,000y, which is the profit contribution of the interior paint, subject to the following constraints. So that's 6x plus 4y less than or equal to 24, x plus 2y less than or equal to 6, y less than or equal to 2, and negative x plus y less than or equal to 1. And our non-negativity constraint, x and y are greater than or equal to 0. So we're going to solve this linear programming model using graphical method. So in order to do that, we're going to graph each of these constraints and come up with what we call a feasible solution. And through the feasible solution, at least one of its corner points will satisfy the objective of this problem, which is to maximize the profit. So let's graph each of the constraints. Let's label them constraint 1, constraint 2, 3, 4. The non-negativity constraint will limit our solution to the first quadrant since x is greater than 0 and y is greater than or equal to 0. So our graphing area is just within the first quadrant, where our decision variables are positive. So this will be our x and this will be our y. So our first constraint is 6x plus 4y less than or equal to 24. We take the equation part, 6x plus 4y is equal to 24. To graph this, we're going to get the intercepts of this equation. So we let x be equal to 0, then the value of y is equal to, so this is 0, what is left is 4y is equal to 24, therefore y is equal to 6. And the second intercept, again we let y is equal to 0. If y is equal to 0, then 4y is equal to 0. What is left is 6x equal to 24. Then the value of x is equal to 4. Therefore, our intercepts are 0, 6, and 4, 0. Plotting these points, so this will be the graph of 6x plus 4y equals 24. And going back to its original inequality, so if we choose 0, 0 as a test point and substitute to this inequality, so 6 times 0 plus 4 times 0, so the left side is equal to 0. 0 is less than 24, therefore 0, 0 is a solution of our constraint 1. And therefore, the solution set of inequality 1 is the one below the line. And the equation part of our second constraint is x plus 2y is equal to 6. So if x is equal to 0, the value of y is equal to 3. And if the value of y is equal to 0, this is 0, therefore x is equal to 6. And the intercepts of this line are 0, 3, and 6, 0. Plotting these points, so 6, 0 is, so this is 4, 5, 6, and 0, 3 is 1, 2, 3, this point, therefore the line is this line. So our test point 0, 0, so 0 plus another 0, so left side is equal to 0 and it is less than the value of 6. The solution set of our second constraint is below its corresponding line. Our third constraint is y less than or equal to 2, and the equation part is y equals 2. And the graph of y equals 2 is a horizontal line. And our fourth constraint is negative x plus y less than or equal to 1. And the equation part is negative x plus y equals 1. So if we let x be equal to 0, the value of y is equal to 1. And if we let y is equal to 0, the value of x is negative 1. So the intercepts are 0, 1 and negative 1, 0. So 0, 1 is this point, negative 1, 0. So negative 1 is here, and 0, y. The corresponding line is since all of our constraints are less than or equal, then their solution sets are below their corresponding lines in this graph. So the common region is this region. This will be our feasible solution. So the feasible solution has several corner points. So we have 6 corner points. So the obvious ones are A, which is at the origin, B at 0, 1, and F on 4, 0. Point C is an intersection of y equals 2 and negative x plus y equals 1. So if y equals 2, therefore negative x plus 2 equals 1. Therefore negative x equal to, transpose this, it will become negative 2, therefore equal to negative 1. The value of x is equal to 1. So that point is, so point C is x is 1 and y is 2. Point D is an intersection of line 2 and line 3. Line 2 is x plus 2y equals 6, and line 3 is y equals 2. So y equals 2, therefore x plus 2 times 2 equals 6. Therefore, x equal to 6 minus 4, 2. Point D is 2, 2. And the last corner point, E, is an intersection of line 2 and line 1. Line 2 is x plus 2y equals 6. Line 1 is 6x plus 4y is equal to 24. So solving for the value of x and y, so first I'm going to eliminate x, so I'm going to multiply negative 6 on the first equation. Negative 6x plus 6x is 0. Then negative 6x plus 2y, that's 12y, plus 4y, that is negative 8y, negative 6 times 6 is negative 36, plus 24 is negative 12. Solving for the value of y, dividing both sides by negative 8, the value of y is negative 12 over negative 8, so that's positive value. 12 over 8 is equal to 3 over 2. So solving for the value of x plus 2y is equal to 6. The value of y is 3 over 2, so x plus 2 times 3 over 2 is equal to 6. So x plus 2 times 3 over 2, so 2 will cancel out, and then 3 is transposed on the other side, therefore the value of x is equal to 6 minus 3, or that's equivalent to 3. Therefore, point E has a coordinates 3 over 2. So again, our corner points are 0, 0, the origin, B is 0, 1, F is 4, 0, C is 1, 2, D is 2, 2, and E is 3 and 3 over 2. And the last part of the solution is we're going to evaluate the objective function through the corner points, and again, one of the corner points will satisfy our objective, which is to maximize the value of p. So at point A, obviously the value of p is equal to 0. At point B, the value of p is equal to 0 times 5,000 is 0, 1 times 6,000 is 6,000. And at point F, 4, 0, the value of p is 4 times 5,000, that's 20,000, plus 6 times 0, that's 0, so the value of p is 20,000. And at point C, that's 1, 2, the value of p is, so 1 times 5,000 is 5,000, plus 2 times 6,000, that's 12,000. So all in all, that is 17,000. And at point D, and the coordinates are 2, 2, so the value of p is 2 times 5,000, that's 10,000, plus 2 times 6,000, that's 12,000, so a total of 22,000. And the last corner point E, the coordinates are 3 and 3 over 2, so the value of p is, so 3 times 5,000, that's 15,000, plus 3 over 2 times 6,000, so that's 9,000. 9,000 plus 15,000, that's equivalent to 24,000. And finally, since our objective is to maximize the value of p, and for this case, the highest value of p is 24,000, which occurs at this point 3 and 3 over 2. So our solution means that in order to attain the highest possible profit of $24,000 daily, ready-mix need to produce 3 tons of exterior paint and 3 over 2, or that's 1.5 tons of interior paint daily. And that ends the solution using graphical method.